So now let's go on and let's discuss how we can show that a linear system has many solutions. Okay, so here we go back to the linear system from 2 units ago. And what we saw in that unit was that this particular system had at least 3 solutions because we gave 3 different vectors that satisfied this system of linear equations. So how do we get there? Well, we're going to apply Gauss-Jordan elimination. And the first step gives us this. And the second step gives us this. Now notice that in the last unit we ended up with an inconsistency here that translated into 0 equal to 1, and therefore we knew there was no solution. In this case, what happens is that this particular equation has absolutely no information in it because it says 0 is equal to 0, and what we're left with in effect is a system with 2 equations and 3 unknowns. That means it's underdetermined. Now if we go one step further and place 1s on the diagonal, we get here. And if we translate that back into a linear system, we get this. And the question now becomes how to identify all possible solutions to this system of linear equations. And this is how we're going to do it. Here's the linear system again. And what we're going to say is, look, we have 2 equations and 3 unknowns. So let's take one of the variables, chi2, and somewhat arbitrarily, we're always going to pick a variable that does not correspond to the first non-zero term in any of the equations. We're going to call that the free variable, and we're going to call the other variables dependent variables. So any variable corresponding to a term that's the first non-zero in a row, that term involves a dependent variable. And what we're going to do is say, look, the free variable can take on any value, and we'll call any variable beta. So beta is just an arbitrary value. Now what did we do before if we found out that some variable had a specific value? Well, in this case not a specific value, but a value beta. Well, what we did was we would go and substitute it back in for that variable in the other equations. So we get this. What we can do is bring all of these other terms to the right hand side, and we end up with this right here. And what I did was I actually moved this beta over so that we now have all of these betas listed above each other. And notice that we can change that into this right here. This here is a vector, and this here is a vector, but each component of that vector has a beta in it, so we can bring that beta outside. Any vector x of this form right here actually satisfies the linear system of equations. This is known as the general solution. We're going to find out that that's not a unique way of writing it, but we'll figure that out later. Now here is our reduced system, and notice that this was equivalent to the original system. Here is our general solution, and here was our original system. And notice that if we take this vector here and plug it in, we end up satisfying the original system. Interesting. I wonder what happens if we plug in this vector. Well, if you take the original matrix, you multiply it times that vector, you get the 0 vector. Interesting. I wonder what happens if you instead had put in beta times that vector. Well, notice that the beta we could have brought outside, and this times this vector would still have been 0. And if you scale any 0 vector by any constant, you still get the 0 vector. So actually, any vector of this form maps to the 0 vector. Interesting. So, what about the other solutions that we came up with 2 units ago? Okay, well, we saw that this was also a solution, But notice that we can write that as these two vectors that we saw right here. That was this vector and that vector. And if we choose our beta to be 1, we get this vector, which we saw in that unit, to also solve the linear system. We had another solution there, and that turns out to correspond to beta equal to 3/2. So we can account for all of these other solutions that we found before. But notice that we actually have an infinite number of solutions, because for any beta, this turns out to be a solution to the linear system. It would be very unfortunate if I asked you on an exam to find all solutions to a linear system and there were an infinite number of them. You'd be busy for a while. So the very important thing here is that although there are an infinite number of solutions, those solutions can be completely described by two vectors. One vector that actually solves the original system, one vector that gets mapped to 0. Later we're going to see that you may need more than two vectors, but the important thing is that you always need a finite number of vectors. So in conclusion, if Gaussian elimination or Gauss-Jordan elimination breaks down, we introduced a 0 on the diagonal, without introducing an inconsistent equation, we ended up with a 0 equals 0 being introduced, then there turned out to be an infinite number of solutions.